years ago, and more recently a PhD student at the Chat Nyangfong have also been involved with this. Okay, so just the background to this attempt to use the code is motivated by the geodynamo, so that's the production of the Earth's magnetic field in the core of the Earth, mostly in the fluid outer core, which is essentially liquid iron beneath the mantle of the Earth, and there's essentially therefore a shell of fluid rather than a full sphere, because the inner core is solid inside this, and it's weakly compressible. But it's very similar. I guess lots of people in this audience are more familiar with astrophysics. Compared to, say, stellar or solar dynamos, it's relatively weakly compressible, it's relatively weakly turbulent, it's relatively more rapidly rotating, but it's not such a different beast. So the style of dynamo action that's involved in there is not a million miles away. A lot of the same constraints apply. And in fact, this approach just tries to do something similar to others, I guess, starting with Wolfgang, with the full convective sphere star in the box pencil code calculations have done, and just simulate this by embedding the sphere in a Cartesian domain in Cartesian coordinates, just extending beyond the sphere you're hoping to model, and damping outside the range of interest. So that's all we've done so far, and this at the end will say a few things that we're hoping to go on to do in the future. And this last thing here is just a bit of a caveat or an apology, because I have been mostly working on other things for the last couple of years, so this isn't particularly new work, and I'm not at all up to speed with the pencil code at the moment, so hopefully if I describe things that can now be done better in the code, people can let me know.
So you only temp you? What
yeah, I'll tell you later. We also damp entropy. So, okay. Okay, so it's fairly standard implementation of the pencil code with log rho, velocity, hydromagnetic, and entropy modules in there, and it uses the EOS, the ideal gas equation state, and well, more or less standard. The important things in velocity are gravity, Coriolis force rotation is strong. Obviously, Lorentz force when we switch the magnetic field on. And in fact, it's not a very compressible fluid we're trying to model, so if we were doing it now, we'd probably be better off just modelling rho rather than log rho. But when we started doing this, the code was in a form where such things hadn't been fully implemented, so the previous runs just took what was there at the time.
Do you add any diffusion to the cosmetic equation?
No, we haven't. We haven't needed it at all. We're very low Mach numbers and weakly compressible. So we're interested in this spherical shell between the inner radius of the inner core Ri and the outer radius of the Earth's mantle Ro, and it's going to just be a polytropic gas, the usual sort of thing with polytropic index is going to be called n. We're running it with gamma equals 5/3, and what we need to do for a sort of sensible ideal gas solution is to prescribe some background state of the gravity and the temperature profile which is driving convection. And the one we've chosen here, which was largely to allow us to compare with a set of solutions we've seen in the literature at the time, by this Tagiata and Sato 1995 papers, used this form with gravity minus 1 upon r squared, G naught constant, and there's 1 upon r dependence in the temperature, and beta is just sort of the strength of that, and it's just normalized like so. And polytropic index is m, which is expressed in terms of these constants in the background state. And as I said, well, as Van asked, U is damped outside to try and maintain U equals 0 outside the shell of interest. And similarly, we do the same thing to S, so that we try and keep the inner core and the exterior at a constant temperature.
So your gravity field is that of the point class, right?
Yes. Yeah.
My experience with this mapping boundaries is that if you damp one, you have to damp all of the variables also, because they might be doing like non-physical things.
The density, exactly.
Yeah. Density field also.
Okay. This is where, in fact, I haven't been running the code for a while, maybe confusing me. My memory is that we don't, but I would have to check the code, and I'll check it later to confirm that we're not. We may also be damping log rho, but my initial memory is not. I mean, the density variations are very weak, so and we're increasing just by, say, 20-30% across the shell, not even a factor of 2. Okay, so yes, we've got the gravity for the point mass, and this is just the background temperature profile, which leaves that in a hydrostatic equilibrium state so that we can look at perturbations about this state. And, okay, outside this, we want to, I'll first describe some plane convection results, but then describe some dynamo results, where obviously we've got magnetic field. It's obviously harder to damp that outside the sphere, so instead we do a similar thing to what Wolfgang and others have done for stars, and just extend the domain out to some outer width. So if the box is radius r, instead of going from plus or minus 1 in x, y, and z, we'll go out to some larger number like 3, just to make sure everything decays away towards the 0, and then hopefully the actual formal condition which we apply for A at the boundary is not that important, just for reference. That's the one we've used here. And well, let me just say, to try and, I mean, obviously using all these grid points in the exterior of the sphere of interest is quite inefficient, so in the first runs we did, we just went out to say x, y, z equals plus or minus 1.5 and just wasted it on a uniform grid, but in later runs we used one of these non-equidistant grids and just imposed a step change in the delta x, delta y, delta z outside some intermediate value of x, y, z, so that in this case this is just illustrated in one dimension. We've got relatively fine resolution in the interior up to say x, y, z equals plus or minus 1.1, outside our shell just radius 1, and then we've changed to just a new linear profile in the exterior domain so that we're not wasting nearly so many points there. And we didn't try and do anything particularly smart with it, we've just gone from one delta x to another with a relatively smooth tanh normal step function shift on the boundary.
It allows you to reduce the number of points outside the shell?
Well, we typically used about the same number of points, but used a bigger spacing so that we can go out to further radius and our magnetic field can decay more, so that the fact we're then imposing an unphysical boundary at this extreme value of x, y, and z is having less of an effect. Okay, there's one thing here I just wanted to say, and again, trying to make this thing more efficient, for a bunch of these runs, though not all of them, we made use of the symmetry in the equator of many of these problems, because just after onset of convection in a rotating sphere, the velocity field is symmetric, mirror symmetric with respect to the equator, and just after onset of dynamo action for such a flow, the magnetic field is either dipole symmetric or quadrupole symmetric, so it is either symmetry or anti-symmetry to the equator. So for some of the runs we've done, we've just solved from z equals 0 to plus 3, say, rather than from z equals minus 3 to plus 3, with this thing imposed at the equator. And this is fine for mildly supercritical runs, but when you start getting serious nonlinear dynamos, the second symmetry of the magnetic field is excited, and that excites the other symmetry of the velocity field, so it's not good for the more supercritical runs.
Yeah, what exactly is the boundary condition on A?
At the actual end.
Yes.
I think it's the one that I've written here. Okay. Well, I've written it here in terms of B rather than A, but the tangential components are 0, and the normal derivative.
The code you have to impose it in terms of A.
Yes, yes.
Okay, so maybe I'll have a look.
Then it's the other way around. You
We'll have
have
a.
the vanishing normal component, and you have stagnating gas. This is not even, so pretty much exchange can and.
Right, your box is Cartesian.
Yeah.
Pseudo vacuum, you can call it.
Yeah. Okay, so just a warning about some of the initial runs with this, which were published with Dave McMillan in this paper in PEPI 2005. But when we first started doing this, it was before the days of the EOS code, and we, I think, were the first people to try and run something without the magical CP equals 1, which all previous implementations of the pencil code had used. which we did just for ease of comparison with the literature, particularly the paper we were trying to reproduce, where they instead, in their equation of state, just had R star equals 1, so P equals rho T. So for this we needed Cp equals 5/2. And so we tried to code this up, but in our first attempts, which were documented in that paper, we didn't get it entirely right. So there was something in the thermal diffusion term which wasn't quite right, which means, if I recall correctly, pretty much just that the diffusivities we quote are not really the ones we were actually implementing. So in this paper, the results are not really the parameters they claim to be. But after the code was improved, and the EOS stuff came in, it became a bit more transparent, and then we expended quite a bit of effort making sure that this scaling worked fine, and ended up essentially coding parallel runs, Cp equals 1, Cp equals 5/2, and making sure that they gave identical results. So the scaling obviously isn't very difficult, but the first attempt we did at it in this paper didn't quite hit the spot. So I will show some results in a minute, and we just wanted to compare them to this 95 paper, and these are just the parameters, non-dimensional numbers, which this used in terms of, well, hopefully all standard variables with the names used in the code, except perhaps D here is just the thickness of the shell, so it's just R0 minus Ri. Radius ratio is 0.3, more or less Earth-like value. Prandtl numbers, 1, Ekman numbers should be low in the Earth. We've taken it relatively low here without inviting numerical difficulties. And Rayleigh numbers sufficient to get supercritical convection, but still leave it relatively simple for these initial runs where we're just trying to benchmark things. And, okay, we ran this. Originally we had this problem with the scaling. After that we sorted that out, but we're still finding that although the sort of solutions we get, which we'll show in a minute, are very comparable to A, what's expected, and B, what these other people are reporting, but we're still finding slight discrepancies. It's slightly difficult to do because most of the results these people reported were the magnetic ones, and for the magnetic case we don't really try to emulate their boundary conditions at all. For their inner core they had a perfectly conducting inner sphere, and they had normal conditions exactly on the radius R equals 1, so we're not particularly close to emulating their magnetic runs, but we should have been close to emulating the non-magnetic pure convection runs. And we get similar behaviour where for these things, typically in this parameter regime, you just get a set of convection rolls aligned with the rotation axis, which at low Rayleigh number, low supercritical Rayleigh number, just drift as a solid pattern, either progradally or retrogradely. But we were just finding that we were getting slightly different numbers of the azimuthal wave numbers, so m equals 4 instead of m equals 5 or so, or slightly different drift rates. And what I think we concluded in the end was that there may very well be a typo in this paper where they state their parameter k, where it's stated in this paper to be this thing here, for which our runs are qualitatively similar but a little bit different. Whereas comparing that original paper with some of the later papers, they do other runs using this value of this parameter, and when we use this value of this parameter, we get a more comparable run here. So it may have been a rather poor choice of benchmark solution at the end of the day. If somebody else knows a better choice of these, by the way, would obviously like to benchmark it more successfully. We emailed these guys. We emailed them quickly at the time that we first thought we spotted this, but didn't get a reply, but didn't chase it up yet. And,
okay, can one derive something like a Rossby number from these sources, or?
Yes, I'm trying to think. It's much less than 1. I'm trying to remember. Yeah, it is just derived. Yeah, it's just derived from this. It doesn't derive from this. It is significantly less. Okay, so just example of what these sort of things look like. I've probably put too many plots in here, so I'll try and go through them without spending too long. So first, before we allow a magnetic field into the problem, we're just doing pure convection. We let it go. This is just URMS. It relatively quickly goes to a stationary value of kinetic energy because it is just in this constant pattern drifting in azimuth. And if you just compare what's actually happening at the boundaries where we're doing this damping, this is just a profile in spherical radius on the equator of the phi average value of two of the background fields. The density rho is in the blue lines here, and the temperature is these red lines here, where the dotted line, at least within the vertical lines which denote the outer shell, is the initial profile. And, okay, that doesn't mean anything outside these lines. I should have just cut it out here, because outside here, damping, etc. happens. But this is being damped, so this thing is 1 at the boundary. It should be being 3. The temperature of the inner boundary here should be 3. It's actually drifting slightly from it. This, I think, was one of the earlier runs where we weren't damping as much as we later realised we did. And similarly, the density is slightly off, so these things are not obviously perfect mathematical boundary conditions, but they're doing approximately the right thing. And by the way, the deviation between the dotted line, the initial state, and the solid line in the shell here is not a problem with the code. This is just the real deviation that occurs with the convection present. So this difference between these lines just corresponds to the fact that we do have convection going on here, and it's altering the background profiles. Okay, so they look fairly boring, so I won't belabor the point. They are just this pattern which is just drifting in azimuth. Here I'm just showing a snapshot. The left-hand side is the Z component of the vorticity. This is the equator of our spherical shell, which is repeated up here, and then we've just imposed these excellent Y planes just so that you can see something of the 3D structure. Now this is the plan form of the vorticity in the equatorial planes, the key thing, and this is the entropy. And for these relatively weakly supercritical things, you just get a pattern with m equals 6 or whatever, which just ridiculous.
And it has no vertical variation.
Oh, it does have vertical variation, I'll show you that.
Okay, but here you don't see.
Oh, it has a weak vertical variation. Yeah.
But that's again because the rotation is...
Rotation is strong, Taylor Prizman is influencing it in as far as it can. And the magnetic field comes in later, that breaks it a little bit, but without the magnetic field, it's just the boundary that is breaking it. Yeah?
Did you try to check how near the center can you model?
Not really, because the we were motivated by the Earth, and the inner core. We were motivated by the Earth, and the Earth has an inner core,
Okay,
which is about 0.35 of. So we weren't really interested in a full sphere, so we just didn't go in that direction. So.
But one thing was to go to the center.
That inner boundary seems to be an octagon here. Is that because there is still some white at the tip of that region?
It is the right on. I mean, these things. Well, it probably wasn't obvious, but from the boundary conditions I gave, the temperature is fixed at the inner core. It's driven from beneath, so the bulk of the action is happening just right on the inner core boundary, and there you do have little changes of direction of vertical vorticity here. So that is a anticyclonic and cyclonic patch right next to each other on the boundary.
But this pattern is migrating azimuthally, so it's not like the grid is sort of imposing the 8 volts, the 8.
No, if you change the parameters, the value of m changes, and I'll show you.
You can get 5 or 7 as well.
Sure, yeah, and well, I'll show you later another plot which it's easier to see the azimuthal drift, and it's broadly smooth. Okay, so this to show you what some aspects of this flow look like in the meridional section. So this is the same flow, but now in a plane of constant phi. So the north pole is here, the south pole is here, and I'm just showing some azimuthal averages. So on the left-hand side, we've got the phi average of the phi component of velocity, and it has a feature associated with these convection rolls just outside the inner core, which is giving you a differential rotation, so that there is some omega effect going on here. But for these mildly supercritical solutions, it's not playing a major role, and if you were going to characterize them in one or the other, they would be more close to an alpha squared type dynamo. I mean, of course, they're generated in 3D and you can argue perhaps more sensibly what's happening in these convection columns rather than making an alpha analysis. But in terms of the classical approach to alpha, which would be related to the average of the helicity, u dot omega, then you've got a nice equatorially antisymmetric helicity associated with these convection rolls, negative in one hemisphere, positive in the other. Obviously strongest in the centre of the convection rolls, and also at the boundaries where the flow is butting right against the spherical boundary and downwelling into the flows, so there's quite a lot happening there in terms of dynamics.
A question?
Mm-hmm.
Do you find an agreement with the Cashwell paper for the differential rotation?
With the KS paper?
Sorry.
I believe so.
They obtain the same slowly rotating flow near the core.
Without having looked at it recently, I don't think we had a problem with this. I think it was a very comfortable solution. I don't remember. You're just comparing with Kageyama and Saki?
Yeah.
Okay, I don't remember, but I think it was.
And what the effective Rossby number of your simulation?
I'll have to have another look at the parameters and let you know later. I mean, I would guess it'd be about 10 to minus 4 or something, but I will, plus or minus at least 1 order of magnitude, because my memory is not right. Yeah?
You don't have an imposed differential rotation or something, right?
No.
Just rotation, uniform rotation.
Well, the whole sphere is rotating uniformly,
convection.
and the inner core and mantle are rotating with it. And then this pattern is drifting progradely or retrogradely with respect to that. But the whole non-axisymmetric pattern is drifting relative to the rotating frame. Yeah? So, sorry, I didn't know there was a movie because but this whole pattern, if you visualize it in the rotating frame, this whole pattern just slowly drifts relative to that rotating frame, right?
I mean, that's something you get from your simulation, that's not something you impose.
Yes, the drift rate comes out. I mean, in the classical analysis of these things, well, at least when you can do it for Boussinesq flows, the drift rate is an eigenvalue along with the growth rate for these solutions. It just comes out. Of course, it varies with radian. Okay, and the main point of this was to get a dynamo, so then we do plug in the magnetic module and allow magnetic fields to develop with this extended domain out to some larger value of x, y, z in the exterior. And I see that this plot, which was obviously designed for a paper, hasn't shown very well at all here. I shall briefly describe it, but all it is a sequence of 4 different runs for different values of the magnetic diffusivity, where it very convincingly shows that the smaller the diffusivity, the faster the growth until you get saturation. Actually, no, this one, sorry, I tell a lie. This one, a single run.
Are you running Linux?
Yes.
Then you could use X gamma to change the contrast. But
I'll show people later.
let's see if told us all about these curves, and we can give you anyway.
Kinetic energy goes here. This is just to go from the single one to the magnetic energy saturates at a higher level.
Maybe we just draw a sketch on the board.
Good idea. So, yeah. And the one on the right, I won't bother to explain, it's just another of these ones showing the background profile of rho P, and this one's, we've obviously damped it a little bit more effectively so that it's closer to the expected values at the boundary. Okay, this one was the one I tried to describe a minute ago, and in line with the sketching, I shall quickly show you that this one just has a sequence of different growth rates of EM with varying magnetic diffusivity, so that when it's the more conducting the fluid, the higher magnetic Reynolds number, the faster the dynamo action. And if you look at the azimuthal average of B phi, it's quite well behaved. It looks quite like the sort of features you get out of alpha squared or alpha omega mean field dynamos. And of course here again, this doesn't come out great, but you get patches of plus or minus toroidal field. Are quite common in these things depending on the distribution of alpha, if it was an actual mean field dynamo. Here around about 0 there's some slightly unsatisfactory events which are just the outcome of this approach of just embedding it in a box and allowing the exterior to the sphere also to have a non-zero diffusivity, but the diffusivity outside the sphere is an order of magnitude lower, but it still allows the toroidal magnetic field to escape from the sphere slightly, which it shouldn't be doing in the Earth, where insulating boundary conditions are much more appropriate for the Earth's mantle. So obviously, the basics of these sort of things are that the flow in the core, the dynamo in the core is doing qualitatively all the right things. It's doing the sort of convection, the sort of dynamo action we expect, but having just tried to do the spherical problem in the box in this way, there's some slightly unsatisfactory things to do with the boundary conditions, which hopefully at some point in the future we can address more successfully.
How much does differential rotation, you were showing earlier that the convection makes some differential rotation. Is this an important part of the dynamo?
It's second order for these mildly supercritical. Most of the action is from things being twisted inside these convections.
Could you just remind me what's the fluid Reynolds number?
The fluid Reynolds number, I couldn't without having to work it out later, so it will not be high. I would guess of order 100, but a few hundred at most. Okay, just to sort of show what the pattern of these things looks like, this is just trying to show the drift of these sort of patterns before and after magnetic fields arise. So what I'm showing here is actually just, we're trying to plot in azimuth phi and time t some feature of this planform of convection. The one we've just chosen to plot here is just the value of UR at one particular point on the equator. So at one radius and point on the equator, we're just looking at whether flow is, UR is going out or going in. We just coded it black or white here. But as the solution drifts round, you can see the speed of the pattern is reflected by this drifting pattern of lights here. And you can sort of see for this one, there's the initial convection which settles down after the transient. Round about here, you get the magnetic field sort of finding its eigenmode and still continuing to grow. And then I believe in these ones, at least one of these, you can see somewhere a slightly different line. For the two on the left, relatively low magnetic Reynolds number, so the convection, the magnetic field when it comes in is not doing much to this, whereas the one on the right is a higher magnetic Reynolds number, and you can see that when the magnetic field equilibrates here, it's totally blowing this ordered pattern out of the water. So you find that this particular way of representing it makes it look like chaos. If you sort of look at planforms at any particular time, you do still see rolls there. It's just their size and number is fluctuating a lot more variably as the magnetic field strengthens and weakens in different places. And just a quick snapshot of what those look like. So on the left we're looking at the velocity basically, on the right we're looking at the magnetic field in the equator, where this is one of these magnetic solutions, obviously, and the colours on the left are the vertical component of vorticity, highlighting these convective cells, mostly near the equator, but with the typical spiral pattern. And you can hopefully see here better the plus or minus cells you get near the inner core.
Don't you think that this is dangerously near the inner?
Sorry, I missed the question. Is the worry of resolution? Or?
That is near the inner boundary, right? So then, how do you know if it is physical, where if it is just a numerical thing, actually?
This sort of pattern is what we expect. It comes out of, at least in business case analytic studies as well. I mean, when you get the convection driven by heating by below rather than heating throughout the sphere, the convective pattern is dominated right at the inner core where the heat's being pushed through it. So we're not concerned about that. I mean, that is the sort of pattern that other people get as well, that is expected for these sort of solutions.
You can also do twice the resolution. Have you done that?
Yeah, I mean, most of these runs, well, when we put magnetic fields in, we're usually using at least 1 to 8 cube, but often just 1 to 8 cube. But for the non-magnetic ones, you can get away with 64 cubed and still get patterns like this quite happily. So. Okay, just to finish the description, the arrows here, which again weren't designed for projections, you can show the horizontal component of the velocity, which is showing the remainder of this convective flow. On the right, we're just plotting all three components of B. The contour here are BZ, and the arrows are BX and BY. And you do get the sort of thing you expect for these solutions. I mean, this thing, although there is a mean axisymmetric field of dipole polarity, basically, you are getting, the field is still dominated by the non-axisymmetric components within the core. And in terms of the magnetic field, you tend to get the flux concentrated within these convective cells, where the fluid is dragged in and goes vertically up inside these convective cells, alternatingly of cyclonic and anticyclonic time. So this is concentrating the B, in a very straightforward way, as is expected for this sort of thing. Except once you get to slightly supercritical values, it is, of course, all chaotic, and it's not happening equally in each roll at any time, and the strength of these things is fluctuating with the magnetic field as well. Okay, so those were our first sort of suite of calculations. We also, I mean, the benchmarking, well, as I described earlier, wasn't great simply because we couldn't find a single appropriate benchmark for all parameters of this code to compare to. There is, in fact, in the geodynamic community a well-established dynamo benchmark, but unfortunately it's implemented for a Boussinesq problem, not for a weakly compressible ideal gas problem. Nevertheless, we wanted, because we spoke to these people all the time and we kept asking about it, we wanted to at least have a go at getting as close to as we could for the current implementation of the code.
And you know that that's original to study the fluid dynamo in the non-Boussinesq case.
Sorry?
That's original to study the geodynamo in the non-Boussinesq case. In the compressible case, a lot of the majority of people use the Boussinesq case.
Yeah. I mean, for the geodynamo, the Boussinesq case makes a lot of sense. So.
Because the Earth field core is a perfect case for using the Boussinesq approach.
Sure. But since, at this stage, we're just doing these calculations compressible, so there wasn't a comparable solution to compare. Okay, trouble with this in terms of trying to just do it with the pencil code for an ideal gas is that the basic state they chose for the Boussinesq benchmark is not in equilibrium for an ideal gas. So if you wanted to try and run this thing in the pencil code, you would have huge problems of density collapsing or trying to get into a state which was more consistent with hydrostatic equilibrium. The sort of cases you can do for an ideal gas, I mean, if you wanted to keep the gravity profile that's in this benchmark, you'd have to impose a different temperature profile. If you wanted to keep the temperature profile here, you'd have to impose a different gravity profile. Of these two, the one above is exactly the profile we've just been using already, so we did just see how important this was in terms of causing deviations from the benchmark. So
how can you get the temperature distribution of 1 over R? In the Boussinesq case, you assume homogeneous distribution of
this is heating uniformly.
Okay.
So it was minimal effort to just choose parameters for an ideal gas. Again, weakly compressible. Again, in terms of the parameters to get as close as we could to the Boussinesq one, these are the values of the Rayleigh number, Ekman number, etc. that we chose to do so. And obviously we don't expect it to be the same because it is weakly compressible rather than incompressible, and we have got this point source gravity rather than the uniform R gravity. But still, qualitatively speaking, it does very similar things. I mean, the real dynamo benchmark is again one of these constantly rotating patterns with m equals 4. We get something which is not constantly rotating, but just vacillates relatively slightly around a pattern. Again, just in terms of the background density and temperature profiles, it's being well constrained at the inner and outer boundaries. It's quite a sensible solution. Again, if you look at the vertical component of vorticity and the density in the equator, it's a similar sort of pattern, but this vacillations showing up here in terms of oscillations between harmonics of the m equals 4 pattern. So sometimes it looks much more m equals 4 than this, but at times like this it's a combination of 4 and 8, but there's something, it is obviously vacillating in this way, but in a form which is still doing exactly the same qualitative type of things as the benchmark itself. So in terms of running it to investigate the dynamo physics of this sort of thing, there's not a problem. Okay, so that's what we're doing at the moment with Abichat and Yanvok in Newcastle, and we're trying to get to ones of slightly more geophysical interest, exactly as Kageyama and Sato and their collaborators continue to do themselves. So, for example, there's a series of papers they did after the one we first referred to. One in 2002 reported that for higher values of the Rayleigh number, but essentially the same solution, they get this thing showing reversals of the dominant axisymmetric dipole field as are observed in the Earth. And these tended to be associated with a particular pattern of dipole, quadrupole, and octupole modes, and almost two possible states of magnetic energy, which helped it. It was when it flipped between one of these two states of dynamo action characterized by some combination of these things that it was likely to reverse when it did reverse. So we've got similar reversals from using the pencil cut in this, and we're just trying to look at those in more detail now. Okay, just what we want to do in the future. So in the short term, I think the first important thing to do is just tidy up what we already did, because in the end it wasn't left in a particularly clean way. It needs to be fully documented and published, and continue to investigate the dynamo physics we're getting out of these solutions. Longer term, and all the things in this list here, people, I know I've already spoken to a couple of people, I know a lot of the things on this list have already been done in other contexts for the pencil codes. So people that have experience with these sort of things I'd be very interested in talking to for the rest of the meeting. I mean, there's been several obvious things we can do to try and make this sort of solution a much better model for the geodynamo. One is to go towards a Boussinesq solution with div u equals 0, or an inelastic one with div of rho u equals 0, and filter out the sound waves altogether, because for the geodynamo they're not important, and it's just a constraint on our time step in these current set of runs. At some point, obviously, now that the spherical coordinates are in the pencil code, we'd like to convert to spherical coordinates. At least for the non-magnetic ones, it should hopefully be relatively straightforward to get convection in a spherical segment, because for these types of convection patterns, the flow in polar regions is not that important. So doing the sort of thing, cutting out the poles, which I know other people have done already, would work equally well in this case. More of a problem in terms of the magnetic solutions is obviously finding good boundary conditions on the spherical surface. So, I mean, I've read a few papers which look as if they might be adaptable for this in the future, but it looks like a lot of work. If other people have already started such work, I'd obviously be very interested to hear it. And I guess there's other minor things which could be done. A less important thing now, but something which would still be useful, would be to make, say, for example, the Coriolis force implicit, because at some stage in the future, that could be the dominant constraint on the time step, and it's a relatively simple term. And, well, this is all still in spherical shells. At the back of my mind for a few years has been the thought that, in fact, it might be more useful in terms of geodynamo research to go to a completely different type of model where you just have a small periodic box representing a small region in the inner core, say in the equatorial region or in the polar region, with the rotation at a certain angle. Because the nature of the turbulence in the geodynamo is still not very well understood, and the nature of turbulence in these numerical simulations is still not very well understood. So I think a lot could be learned from doing these periodic type box simulations motivated by the geodynamo, but ideally once we were already in the right parameter regime with, for example, Bushnell's code. Okay, thank you for your time. So we lost the chairman, so okay.
Is your time step currently determined by the exterior 10 times more diffused magnetically?
Well, we picked 10 so that it wasn't
but basically, if you could use 50 or 100 instead of 10, you would be probably sufficiently close to the insulating boundary conditions.
That's true. Then of course we would. For 100, I suspect the time step would be a problem, but we didn't try and push it.
But if you wait till Friday, you will find that it might not be a problem.
Okay.
You can probably get a factor of 20 in the diffusion time step, and thus you could up your external diffusivity by a factor of 20%.
Excellent, sounds good.
That's not it for frontal types, even yes.
Your 10 regions look truly large, right? You know, how many fluid points you are using there?
In the external region?
Yes.
For the magnetic ones, 2 million.
Yeah.
So, I think...
Like what, like 50%
No.
of your fluid points? More?
I think because of the volume factor, I think it's more like 70.
Yeah, so it means that you can move through spherical coordinates and you will see that quite much.
Sooner the better. Of course, the magnetic boundary condition in spherical coordinates is not clear anyway.
So why does it actually have to be so large?
Well, we were being conservative. I guess we could probably get away with less. We did a suite of runs first, and I think most of the runs we did were about I was 1.5, so X, Y, Z to 1.5, because our gut feeling, although I don't remember now the diagnostics which led us to that, was that anything less was. If you think that this thing's decaying at R squared, if you only bring out 0.5, it doesn't sound like this.
So what do you think about doing it unelastic? I mean, there's certainly great interest in these things, and we would either use the Fourier transform method, which of course is in place, but it would not be possible to run this on very big machines and perhaps at some point.
This is in the Poisson solver or otherwise?
That's the Poisson solver, yes, Poisson solver.
Yeah. So
maybe that's at least worthwhile to implement to see how good that is. And the other method would be to carry on with the highly good solver that Hoffman started.
Well, I never looked at that at all. So.
But it does not work, it does not paralyze.
I mean,
Not yet. I mean,
Is there no better than Poisson solver? Is it possible to implement?
It's sort of clear how to parallelize that's work that needs to be done.
This is the Poisson solver or the multi-grid?
The multi-grid Poisson solver.
Okay.
Do you know whether it's fast compared to the Fourier solver?
That's another thing, but that's
I
probably
think
the first
people
thing.
normally say that Fourier solver is about the fastest way to go. Even, I mean, obviously it has limitations with geometry and so on. But people normally say that if you can do, if you have a choice, then the Fourier solver will normally be faster.
But the problem is if you go to very big machines. I mean, the largest was how many processors for you?
128.
120, that's not too much, of course. I mean, the plan is to go, of course, eventually to the several thousands processors.
But would this be a problem with the Fourier solver?
Yeah, I always think so. So we have to do the global transpose and stuff all the time.
Yeah, but if you have a good enough network, I don't see it as a problem.
Okay.
And of course, if you were to go to 1,000 processors, you would have a problem that really fit in there. So, and I don't think communication would be
By the way, we're using FFT pack for the Fourier transform, right?
Yeah.
Would there be I mean, we could use FFTW or something.
But that can only parallelize along one direction. FFTW only parallelizes along one direction.
But we do the parallelization, right? I mean, we use FFT pack also only for one dimension.
No. We do both. No, I mean, FFTW can only parallelize along.
No, I understand, but don't we do the transpose ourselves?
We do the transpose by ourselves, but FFTW strengthens exactly that they do the transpose in a much more clever way.
Yeah, okay, but I think, but for 1D, if we only do 1D FFTs in the code, right? Well, in effect, we do 2D
But
the FFT algorithm is only
the FFT
applied
algorithm,
along.
the FFT algorithm is not the problem. The problem is transposing the array. That's what the problem
No,
is.
I understand, but I'm saying we can substitute any 1D FFT algorithm we like. We could use any 1D FFT algorithm.
Yeah, and there I don't think we will find something much faster.
Than FFT pack. Well, I'm just saying. I mean, I think FFTW is faster than FFT pack.
Even the 1D.
Even the 1D. Yeah.
Okay.
Or Intel MKL. I mean, they're highly optimized FFT routines, so I think it would be good to have a write a wrapper
I think so.
or something like that.
Yeah.
That one can talk
But
about.
actually, the wrapper is already there, right?
Yeah, so it wouldn't be a big
doing
deal.
a Fourier underscore FFTW, and then you could.
Yeah.
So it just be matter of doing it.
Yeah, no, it's not a big deal.
But I mean, all the Fourier transforms rely on having one direction where you have the no partitioning over CPU. So if you really want to use it on these very large machines where you estimate that we need to distribute in X, then it sounds like that's just no longer an option.
FFTW in principle has at least one algorithm which parallelizes even if it's over multiprocessor in X direction.
Well, last time I looked at it, it looked like you basically from the algorithm you can only do it if you have all the data in that direction that we.
But I think, and it possibly hasn't changed because the MPI version is a couple of years old and has only been maintained.
The MPI version is not maintained actually.
But is there any way to do FFTW, FFTs with three parallelized directions?
I doubt it because it's a highly non-local thing. I mean, of course, you can communicate all the data that you need.
Yeah.
But I'm skeptical about being able to do that efficiently.
Yeah.
But we could then, of course, have an auxiliary array.
But you would need an array of length mx, even if you were subdividing x into mx divided by 18.
You would need that, yeah. Yeah.
I think so.
But basically, something like instead of transposing, you just copy the data the full pencil in that direction into that array, and it doesn't have to be a one-dimensional thing. It can be it can have a certain cross section, it can be a beam, a bar, whatever. And then you do the Fourier transform there, and then you put the stuff back. You don't have to transpose then you just do that for all directions, something like that too. I guess
That ought to work. And then you would do the same in Y and in C. Yeah. It would just be
communication-wise, it's probably comparable to what we're doing now.
I mean, what I do with self-gravity, it kind of slows down the flow by factor of 2. And I think it's mostly communication. The FFT itself is extremely cheap. It's just n log 2n. So the problem is
with some prefix.
Yeah, but it's still pretty cheap. The big problem is transposing and communicating.
But I mean, it's n cubed in a sense, depending on what you define to be n.
Yeah.
So it's comparable to our derivative operators, which normally, at least without parallelization, eats up most of the time, times some logarithmic factor that's probably not too large. But that logarithmic factor together with an unknown prefactor could be anywhere in the range of making this dominant or making this.
But I guess we're not scared of making the code lower by a factor 2. We're scared that it would be a factor 10. And I don't think it will be factor 10.
Are all of these FFT packs open source if we're putting the code to?
No, they don't do this.
No.
They don't That's why I think using a T-pack as the default would be fine, but having actually a wrapper for the T-pack, for ST, using a T-pack, the default is good, and having a wrapper for STW is good also.
Maybe we should discuss briefly how we would arrange it in practice, because the way how one does it is by writing the equation in terms of. So I was wondering whether there's a practical way of doing this. So we have the right-hand side of the equation. Let me write it as in this form. So it's the d. So normally we write the equation in this form. So we have the minus. We actually call it part h here. And then we have then the rest we can call f. So that's important to split these two. And then of course f, what that is the sum of. It includes, of course, everything. It includes u dot part u, and plus maybe gravity, and so forth. Plus viscous force, plus maybe an external forcing function. And so then what we want to do is we want to take the divergence of this equation. We want to put the multiply by rho inside, of course. So then it's slightly different. Then we want
For an elastic.
yes, we want to put the rho inside.
Well, for me, Business would also be of interest.
Anyway, this one is still correct, and then this one is just slightly different. This one is then become J U I U J. That's all. And then we take, of course, the divergence of this. And then we have 0 is equal to minus del squared of h plus the divergence of rho times f. And that's our Poisson equation. And from that we get h. And then after we have h, we put it back in again, and then this is how we advance this equation again.
The inelastic.
Yeah, that's exactly how it has to go. So in other words, we replace the continuity equation, we remove the continuity equation, and then we somehow must suspend the calculation of h, must wait, and must calculate the right-hand side without the h, And then at some point we take the divergence horizons, multiply by rho, take the divergence,
But I mean, can't you just
send it into the solver, and then add this back in again and resume the calculation, the final step of this calculation, and maybe d by t of this. And that can be done at every sub-step.
aren't you just saying that H is the inverse Laplacian of something?
Of course.
So why do you have to suspend the calculation of continuity?
Because we need to calculate u, of course, the time derivative of u. So that means we need to know this and this.
Yeah, sure.
And we can. So if you wanted to calculate this, then we want to at least save rho times f, of course. Maybe that could be done.
If we have something to do this, then possibly we can also run fully incompressible run.
Yeah. But it would work, I think, according to the same method.
Yes.
But,
Just
I
as in
thought
Bohr's
Boris had coded something like this, or am I thinking wrong now?
Boris? Yeah?
Didn't you do something with an elastic approach in the pencil code, or was that with another?
Yeah, I would like to do that.
You would like to? Okay.
I would like.
Okay.
But I mean, wouldn't you just after you've updated the F array, calculate the inverse Laplacian applied to rho times F, and store that in an auxiliary slot of the F array, and that would then be the H that you use in the next step?
Yeah, I guess so. So that means, so when we calculate pencils, we just have a dependency, yeah? Or something. Yeah.
I think you have to do it after you know everything, because this is a global thing. So you cannot do it pencil-wise. The inverse
The whole right
Laplacian.
hand
Yes.
side has been calculated.
Okay, so that means we calculate this outside the pencil, just like radiation transfer and everything.
After each sub-step, you would
And then we would sort
But without the grad H. You know df, including the grad H.
no, you're calculating the one for the next time.
No, what, next time? No, at the same time.
For the next time step. For the if we go from time
Yeah.
10 to time 11,
Yeah.
then we need grad H for time 10, because we have an explicit key. Well, I'm talking about a substep only.
You're also using F for time 10 and H and F would be at the same time.
So before doing the next substep, we need H for the current time, or the starting time for the substep, and that we can do by immediately after the previous time step having stored the inverse Laplacian of gradient rho f, divergence rho f in that auxiliary slot. And then the whole F array we have is consistent, because it has all the F array variables that have an equation, and it has the additional slot that is in sync with the other slots.
This is exactly like radiation transfer, isn't it?
So why?
I guess it ought to be, yeah.
But why don't you say we do it at the beginning of each time step? I think we should do it at the beginning of each time step, calculate the F, put the F into a three-dimensional auxiliary array, calculate then the Laplacian, or the inverse Laplacian, put that into a pencil, and then begin the pencil, the rest of the pencils.
I guess
Must be the
we're
same.
talking about the same thing.
Yeah.
It's just where you actually your way of describing it is better, because it tells you how to get started.
Okay, so in principle that's of course obvious to do that. But you want to do it?
Well, I'll have a look at the code. I think I'll need to speak to understand.
So the only thing that stops us from doing this is a parallel multi-grid solver.
I would first of all do it with the Fourier solver, because that's really
Yeah, I
hard.
think preventing us from doing it in parallel. Only if we wanted to parallelize on three dimensions, then you would have to start thinking about how to do that. But if you want to parallelize on Y and C, it's fine.
By the way, I think there are various subtleties when doing this in the shearing sheet.
Yes.
Because in that case, the time graph operators do not commute. So diff of du by dt is not the same as d by dt diff u. And that
well, you get a couple of extra terms, but you also have to be careful to conserve the order of to maintain the order of the time stepping, because you can. What you want to achieve is that the time derivative of du by div u is 0, but that's non-trivial.
I see.
I think.
Why is this the problem in the sheet?
Well, I see that is a problem.
But it can be done. It can be done. I've done it in the spectral code, the shearing sheet code, with the same problem exists.
I mean, all he's saying is you have this, and if you take the divergence of this, then that's no longer, is that really obvious? So you're saying, well, that the divergence of d rho by u is not the same as the order vector, which in this case is positive.
Exactly. No, those are clearly not the same.
Is that, I don't know, yeah.
Why is this not the case? Why is that not the case? I don't see that.
Because, let me check.
I don't know why it doesn't. I think what's happening maybe is that here there are some non-trivialities. Because there was a road inside. But you can certainly write it for the full velocity field. I was saying, and then
Sorry, I think I may have, that's what I said would be true in shearing coordinates, but we are not.
We're not in shearing coordinates, yeah, I think that's okay then. But we are maybe when we do Fourier transform.
Just for the one.
Yeah, it's a band just for the Fourier transform.
Just for the one.
Yeah, right. So everything is okay, yeah. Great. So then that's the way to go, perhaps. I think going to the Fourier solver first is a good thing, so that we have an elastic version and it works only in a certain circumstances, but
that absolutely makes sense. One constraint of the Fourier Poisson solver is that right now it assumes periodic boundary conditions. One can have variants with sine and cosine transforms where you impose seriously or Raman boundary conditions. Multigrid is in theory more flexible, but then I guess it's probably not that much easier to get the boundary conditions that you really like to have. But still, as a first step, that's perfect.
For the moment, the Fourier solver, the two directions are very big.
three.
No, two.
No, there are two directions, the horizontal one.
The south is the third direction by inverting and a trilinear.
Okay. Is that you explain that?
Huh?
You're doing that?
No, not, but it is implemented.
No. What? Implemented?
It's implemented. That's what you call what combined to something semi-spectral.
And the Poisson solver solves Laplacian variable equal to right hand side.
It gives you the inverse Laplacian of whatever you really can.
Okay.
It
shows that we have also steps.
it's completely general. It's not hard to together with the subversion of it.
And the right hand side, it's a fancy or
Right now,
So it has to be a local field because there's no good thing that you
so you have to stop the visualization when you solve the Poisson solver.